I have gone back through and I watched all of my videos pretty much over again, and then I clipped it up and I kept all the stuff that I liked, and then I went through it again and took notes on the video on the clips and basically consolidated everything down. And the first thing I want to say is that all these videos and everything I've been saying has been more of a speaking my thoughts aloud and kind of a proof of work of what I'm going through here. Because what I found going back at my videos is some of the stuff I said, I was like, what the heck was I thinking when I was first talking about this, right? But the reality is I had no idea what I was talking about. And in some cases, I still don't, obviously. So I'm not crazy informed on all of this stuff. But I've been slowly working through everything, and a part of me is a little embarrassed by some of the stuff that I've been saying, but at the same time, I don't want to get rid of it because it's kind of a showing that I didn't, if I finally get to a workable solution that everyone agrees with, it kind of shows that I didn't know what I was talking about before, and I want people to see that progression, to understand that, hey, I could do that too. Maybe that's being a little full of myself, but we got a plan for the future here. So, basically, I did all of that, and now I'm going to go through and make better videos that hopefully more people will watch. But I'm still going to do these because I still have some things I want to speak aloud before I consolidate them back in again, and then try and make a better video about it. Because like I said, some of the stuff that I came up with because I did this. I didn't just think of it until I was talking about them. So that's kind of what I'm trying to do here. I mentioned that higher energy light should have less mass. And I finally noticed that this is exactly what we see in Hawking radiation. I think it's a thing that I brought up in the past, but the thing that I realized, is that, as a black hole gets larger, it increases in mass, right? Its radiation is a lower wavelength. It gets redshifted, right? But when it's smaller in mass, it's a smaller black hole, it gives off blue radiation. It has a higher frequency. So it's almost like a proof of what I was talking about in a sense. And the reason why, that may seem like, oh, well, that's completely different. That's Hawking radiation. But this gets into a whole black holes and stuff are really just matter at a greater scale. And that radiation is akin to what we see as radiation, just on a scale that we can't comprehend. And so I just wanted to kind of point that out and mention it because I thought that I had that realization. I wrote it down here, and I wanted to make sure that that was somewhere, just in case. Another point of potential evidence. Not that Hawking radiation is actually technically proven, I guess, but theoretically possible, and it just goes to show that I'm not, just making this all up. Well, I am. But at the same time, there's some thought here. At least I think there is, So, that's that. Anyway, peace out. So, I haven't really done a lot of talking videos in a little bit. And I believe it's because, well, not. I know what it's because. I know because, one, I wasn't really feeling it. I kind of got demotivated because I was like, feel like I'm just saying a lot of the same thing. And I felt like I needed to reassess and focus in a little bit on what it is I want to say here. If I try and do everything, then no one will understand anything that I'm trying to say, is my problem that I've realized. However, there are still a couple ideas that I still have here that I'm now going to do some talks on, because I went back, consolidated everything, kind of reaffirmed what exactly it is that I think is going on, and kept what I thought made sense, and I'm working on putting all of these things together. And the goal is, in the long run, there'll be a series of quick. My goal is to make them animated because I think it would be funny, at least for me. So my goal is to have them animated. It's a little more engaging. It's going to be a little more fast-paced, to the point, not a lot of fluff, not a lot of pauses and thinking going on. More of a, this is what I've got working here. This is why, clear, to the point is the goal. And the hope is that those will be more engaged with, because there's not a lot of fluff there. There's a little more of an interesting thing to look at than just me sitting here talking. And so, in theory, people will want to listen. And if they don't, then it's whatever. I've pretty much decided that if no one listens, nobody listens. But now it exists somewhere. So at least I could say, well, I tried. Because I don't know. I'm really torn between, am I a genius or am I crazy? And I've said it before, but it's hard to know for sure, because pretty much the definition of what makes a person a genius is thinking outside the box and coming up with an idea that didn't exist before. And that also means that you're going against the grain. No one else believes you until you make them believe. And so pretty much I'm hoping that, like to myself, I am confident. I'm so confident right now that it just works. It just makes sense. I feel like I can't be wrong. But there's obviously some things which I'm going to do some talks on where I had to do some apologizing because, well, I was wrong. Or at least on parts, right? So my lack of understanding leads to me not understanding, obviously. And so that's why I'm doing these talks. That's why I'm working through this. And one of those examples is Rayleigh scattering. And I did a video, I don't know which video it was in exactly, that I said, hey, the sky's not blue because of Rayleigh scattering. It has nothing to do with that. And that was wrong. All right, that was wrong. That's my bad. I didn't really understand Rayleigh scattering, and I still think that the reasoning behind Rayleigh scattering is wrong, but there certainly is some kind of scattering happening. I just really don't like wavelengths. But at the same time, I think they do exist. That's another thing that I came back to, is that wavelengths do exist. However, it is not the photon itself that is that wavelength. The photon is a particle still. It's like, what was the, I said it before, but basically, imagine you have a bucket of particles, right? And when you shoot a photon into it, it makes a ripple. That ripple is the magnetic waves. We take these magnetic waves and say, oh, electromagnetic waves. And that's because an electrical force, which is just a particle, moving through space, is creating a magnetic force, which is the movement that results from this particle moving through space. And so this action and reaction that we see, we go, oh, electromagnetic wave. However, that entire process is driven by purely gravity. And so really, it's nothing more than a computational or comprehension tool. It's kind of like using the Bohr model to understand the atom, even though it's wrong, right? And funnily enough, I kind of want to go back to an orbital theory, not exactly like the Bohr model, but an orbital theory, kind of emerging between orbits and what we have as electron clouds. I want to do a MASH meet in the middle somewhere is pretty much what I want to do. And this is really not even a topic. This is just a accumulation of some concepts here. But the main thing I wanted to say, I believe, was that I'm consolidating, and not everything I say is correct, but I hope in the long run I come to a conclusion that is. And I'm a part of me is embarrassed with some of my ideas initially, but it's also, I think, important to show progression and eventual comprehension and being exposed to new facts, internalizing them, and then coming to, the inevitable conclusion that, hey, I was wrong here, right? And the fact that I can come to the conclusion that, okay, I was wrong here for this, leads me to a more confident position with other things, because it's not that I'm trying to be, I'm different, I know what's best. It's that I truly think we're wrong here, right? And so, as I'm working through this, I can admit, okay, I'm wrong. But I also think that I'm right. And I don't know, it's tough because I'm always fighting with myself, because I feel like on one hand, it's foolish to be so confident, but on the other hand, if you don't have any confidence in your theories, we'll never progress forward. So that's why I'm still making these videos. That's why I'm hoping to teach something, if anything's worth anything. Right. And yeah, the reality is I have no idea what the initial point of this video was. It wasn't supposed to be such a long rant there, but I guess that's what we did. And so, in this video, I'll just talk on a quick thing, because really what I do want to dig into Rayleigh scattering, but I feel like that is going to be a long video, potentially, of me talking through that. And I touched on it here, but I'm going to go a little more into the weeds in the other video. So what I'll say here instead is angular diameter turnaround with galaxies. So this is something that I found out about while watching a video, is basically that there's like a certain point where galaxies that are far away start to look larger again. And so it goes like, oh, close galaxies are large, and then they get smaller and smaller and smaller as they get farther away. And then at a certain point, they start to get bigger again and get bigger and bigger and bigger. And as they're more redshifted, right? And so we assume that things that are more redshifted must be farther away, because the current belief is that because of dark energy and spatial expansion of the universe, as this light travels, its wavelength gets stretched out. And I personally think this is the stupidest thing. I don't understand. I don't like it. Period. And I know that it's not great evidence, but I don't like it. I don't understand how that makes sense. And so what I think with light getting redshifted, it's not that I don't think light is not redshifted. I just don't think it's getting stretched. I think that that's dumb. What I think is happening is that as energy travels through space, it just loses energy over time. And so naturally, as it loses energy, it gets to a larger wavelength. And so it becomes redshifted because it's traveled so far. It appears to have taken less energy. And we just see this with anything. Anything loses energy over time as it, travels in space. You throw a ball, and that ball will not travel to infinitum. It will fall into some gravitational well and get stuck there, or it'll just lose energy in a gravitational field and stop there, right? Like like if you throw something into space, it doesn't continue forever. That's not real. That's not how it works. It can go far, but it doesn't go forever. And things lose energy over time in space because energy gets just there is no rest frame. So there's always a bigger gravity well. If you know what I'm saying. And so getting back to what I'm talking about here is getting into this whole gravity thing. Basically, I think the way that gravity works is kind of similar to, it's not that I think this is just what we observe. Atmospheric pressure at sea level is greater than it is on top of a mountain. And the pressure of water 10 meters down is a lot higher than it is right at the surface, right? Or like right below the surface, I should say. And so we know this is the case because, gravity is pulling all this down, and so all of this compounding weight on top is pushing down even harder. So the farther you go down, there's more stuff pressing down on it. And because of this, I think it's logical to say that the density of the atmosphere and any fluid that's, like say in a lake or in the ocean, as you go down, the density is increasing. Because as pressure increases, it allows for higher densities. And so that's just basically what, honestly, atmospheric pressure is. It's just an increase in gas pressure, but density of gas. There's more gas around, so there's more pressure, right? And so because of this, we can almost see it as layers of like the strength of gravity. We can use it as a dividing line, right? From 1 atmosphere to 0.8 atmospheres is like gravity is like this strong, right? Relatively speaking, all right. We do it with the electromagnetic spectrum, right? The separating lines are things we made up. There's not like, there's a wall here. That's not how it works. So we could do this with gravity as well if we really wanted to, right? And so gravity is this strong from this height to this height, and then gravity is this strong from 0.8 to 0.6, right? Atmospheres. And so we have these different gravitational strengths going all the way up to no atmosphere, right? Basically out in space. And using that logic, right, when you're throwing a ball, or we'll just jump right to light, because I've done a demo here, and you can look it up. I'm sure other people have done it. I know other people have done it actually, but basically you shoot a laser through I've done it, but you shoot it through a laser. You shoot a laser through sugar, dissolved in water, and there's more sugar per area of per volume of water lower down than there is higher up, and so because of that, there's a different density. It's almost like shining light through different materials. You shine light in water, it gets bent, right? We call that refraction. Effectively, this refraction, if you have multiple layers, right, it gets bent, right? And so what happens in these layers of density is when it's a gradient, right, you can say there's infinite layers, right? If there's no dividing lines, there's infinite layers, and we can basically say it's a gradient, and there's infinite layers, and it's just gravity. It's just the strength of gravity is really the main factor here, right? And so when you're shining the light, it gets bent, 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 and eventually, instead of continuing up, it starts to level out, and then it gets bent back down. And so, what I'm saying here is that light does this in this mini demo in sugar. It does this in our atmosphere. I'm so confident in this. I feel like it should be the common belief, but I don't know if it is. And what if we go outside of our planet, right? We go to the universal scale here, and we are looking at galaxies off in the distance, right? And in the same way that we would look at light or like an object in the distance, it seems to get smaller and smaller and smaller, right? The way our planet works is we're looking out at the horizon, but we can't see through solid matter, right? But in space, that we have our horizon line that we're all on, but at the same time, there's not really that solid ground we can't see through. So we can still see these things that we wouldn't be able to see on the Earth, right? Because it's not a one-to-one comparison. But we can see these things that would be over the horizon on Earth, but in the universe, they're technically over the horizon. Now they're under the horizon, but we can still see them because there's nothing actually there to block them. And so as things approach the horizon, they get smaller and smaller and smaller and smaller and smaller. And then as they fall down, right, past the horizon, they get larger and larger and larger again because it gets easier and easier for the light to get to us. And the reason for this seems ridiculous, but I kind of noticed this phenomenon when I was doing my sugar experiment, and I looked back at my videos, and I don't have a video where I actually talked about it, but I pointed it out to, I noticed it myself, and I was like, what the heck is going on here? And I pointed it out to, I think, my friend, or maybe my, siblings. I was talking to them about it, because I was like, this experiment's so cool, you gotta look at this. And they were like, whoa. But, I was shining the laser kind of at an angle where the density was strongest, and so I was shining it, it would go nowhere, and then I would tilt it up just a little bit, and the laser would come up and then get bent down, so it would go whoop and go that far. And as I raised it higher, it would move out, right? But as I got to a certain point, then it would come back in. And as I kept raising it up, it would come back in and then start going back out farther as I was raising it more. And it seems so weird to have it kind of do this sort of pattern, right? Where it was going, it seemed to almost go farther for a little bit before it started coming back again. And I thought that was so weird. I was like, why is it doing that, right? And what I realized is that as you keep lowering it down, right, the light is no longer getting bent as it goes through different gradients, right? Instead of the light going up and getting bent, and then falling back down, what's happening is it's getting bent, and then it's just staying it doesn't have the trajectory to keep going up anymore, and so it keeps in the same gradient. And since it's in the same gradient, it doesn't get bent down, and it allows it to go a farther distance out, because it instead of hitting another gradient and causing that refraction, it maintains itself in the same medium, and it's almost as if it's in normal air, right? Relatively speaking, right? If there's no other gradient, that's now the new normal, and it just travels through it for that distance, for however far. And so because of that, while it's inside, that range, it's getting bent less. It has less like refractional bends because it's going through fewer gradients, or fewer levels of the gradient. It is allowed to go farther out. And so, long-winded here in my explanation, but this is supposed to be quick, but obviously I had very little written down, but I guess I had a lot to say here. The light travels out a farther distance, and the only reason why it starts to fall back in is because we start to have ground, and so as the ground becomes a thing, it no longer can just keep traveling out. And as I keep shining it, it falls in. But with the way that our universe works, and the fact that we can see under the horizon, potentially, I'm saying potentially here, this is not, proven or anything, but I think that it should work like this. Then more of the light is able to make it farther to us than at the horizon, because basically that point where it switches from getting smaller to getting bigger again, that is the horizon line, right? So anything that's on that horizon line is going to be hard to see, because most of that light is getting bent into trajectories that are either above us or below us. And so only a little bit of the light is making it to us now. But as it gets below the horizon, it's now shooting up into a gradient, and is able to travel farther in a single gradient. And it appears to get bigger and bigger and bigger again, because more of the light is able to make it to us for us to see it, even though it's getting farther away. And so, I thought, hey, that's really interesting. And I mentioned that potentially blue light, what if a blue shifted thing is just something that's actually really far away. And I still think that is possible, but I'm uncertain about it, and I don't know how we would prove it, right? Maybe everything we think is blue shifted is really stuff that's farther away, and it's not that it's moving towards us or anything like that causes it to blue shift. I don't really know. It could be a combination of both. It could be I think most likely it's a combination of both, is really what it comes down to, is that there's a combination of both. And because this was all in this video, which I just realized because this is 20 minutes long now, I think that Rayleigh scattering and this whole gravity that I'm talking about, the video that I was talking about this, I was saying the sky is blue because of gravity bending blue light less significantly, and so it's the only light that's actually still up there. I think that is a factor. I think that that's important. I think that things in the distance look bluer because, one, Rayleigh scattering, but also because more of the blue light is able to reach our eyes than the red light, because some of the red light is falling off. I think it's a combination of both of these things, and pretty much all of my theories are either a combination of something new with what's existing, or is what's existing but interpreted a different way, or just addressing things that were kind of ignored, but already were a thing. That's a majority of what I'm doing. Nothing too crazy. So, yeah, I think we'll end that here. Peace out.